All right, so chapter 9. You might be familiar with the Hindenburg, maybe as just a saying or an idea, but it was an actual giant blimp that was filled with hydrogen gas. It tragically burst into flames and killed 36 of the 97 passengers. But what makes hydrogen so flammable and reactive? Because we also have helium balloons, and helium balloons, when you pop them, even with a flame, don't catch on fire. Helium doesn't burn, hydrogen does. But they're on opposite ends of the periodic table, but in a sense, they're right next to each other, right? They're very similar in a lot of ways. But that's why we fill modern blimps with helium rather than, there you go. Now Zoom has the camera. That's why we fill them with helium, so that they don't catch on fire. But why is helium inert compared to hydrogen? So we're going to be talking about that. Ultimately, it comes down to electrons. So if we take a look at a periodic table, this is sort of getting into the periodic law. Hydrogen, very reactive. And if you remember all the way back to like chapter 3 or 4, we talked about sort of the different series on the periodic table. The columns represent elements that are all very similar. So hydrogen is highly reactive and flammable, but so is lithium, sodium, potassium, rubidium, cesium, and francium, all very, very reactive. So are beryllium, magnesium, and everything in column 2A. And then if you go over to the other side of the periodic table, helium is a noble gas and is inert. And all of the elements in that column are also inert. So they don't react with anything. This is kind of a hint that there's something about the way the periodic table is set up that might explain that. So models and theories can help, are part of that explanation. We're going to talk about two different models of the atom and more specifically electrons. The Bohr model is the first one that we're going to talk about, and then we'll work our way over to the quantum mechanical model that propose explanations for why the elements act this way. And also explains periodic law, because why is it when you arrange the periodic table in this way that these patterns emerge? So we're going to cover a lot of definitions up front here, and I'll try to highlight the things that I think are really important that I might test you on. These quotes are really good, though. Anyone who is not shocked by quantum mechanics has not understood it, because, if you've seen the Marvel movies, like the Ant-Man movies, it's like, don't go to the quantum realm. That's because, laws of nature that apply at, the macro scale do not apply at the quantum realm. So they got that part right. The quantum realm is freaky, which is why I like Schrodinger's quote here: "I don't like it, and I am sorry I ever had anything to do with it." Erwin Schrödinger is the guy who came up with the thought experiment of Schrödinger's cat. And then Albert Einstein said God does not play dice with the universe. So even though it is hard for us to comprehend the quantum realm, there are rules that apply there. They're just different from the rules that we're used to. The quantum mechanical model is foundational to modern chemistry. That's what a lot of stuff is based on. That's our best understanding of why electrons act the way they do. It explains the way the periodic table is, guides our understanding of chemical bonding. Again, comes down to electrons. And then you can also, or its applications include semiconductor devices and design of new drugs. So one of the weird things about quantum level stuff is that you can have something called quantum tunneling. So electrons will just pass straight through solid objects. And actually the memory chips in your phone use this property to store electrons in bins that represent ones and zeros, and that gets read off as pictures of your dog or cat. So to understand electrons, we're sort of going to take one step to the side and talk about electromagnetic radiation first. which I think electromagnetic radiation is really cool. I'll have a bunch of asides about this, just cool little facts. But light is a form of electromagnetic radiation. Light is not matter. And so light is electromagnetic radiation. It is not matter. But instead, light is a type of energy that travels through space at a constant speed of 3 × 10⁸ meters per second. It's 186,000 miles per second. And I think I mentioned this before, but so the distance between the Earth and the Moon is about 250,000 miles, 248,000. That space, you can fit all of the planets side by side and have room left over. An electron can travel from the Earth to the Moon in just over a second. So the entire distance of all of the planets plus some, and you can get back in just over another second. It's very, very fast. And light has properties of both waves and particles. So light is, well, the wave-like property of light is kind of like the surface of water. So if you throw a pebble into a still lake or a swimming pool or something, it creates waves. And those waves move out, and those waves have energy that was given to them by whatever hit the water. Light is the same way, just super fast. Right, if you use the flash on your phone, as soon as that light turns on, it's sending out waves of electromagnetic radiation at the speed of light. So they can carry waves, or the waves can carry energy as they radiate out. We got two different terms that we use to talk about just generally electromagnetic radiation. So there's different types of electromagnetic radiation. Well, yeah. We categorize electromagnetic radiation based on its wavelength as one quantity. So it's the distance between the adjacent wave crests. So going from the peak here to another peak, that's the wavelength. So it's how spaced out the waves are. And for visible light, the wavelength determines the color, usually in nanometers. So if you've ever tried to buy a laser pointer, you can get, or you at least used to be able to get red, green, and blue laser pointers, and they all have a different specific wavelength that they produce, because a good laser only produces one wavelength of light, which is a rare thing, as we'll see. So most light sources that have white light contain all of the colors. Right? Every wavelength of light is in there. So when you shine it through a prism, those separate out. If you take more physics, you'll probably talk about why they separate out. But you can separate light into these different colors and different wavelengths. One of the things that blew my mind when I first sort of learned about electromagnetic radiation and light is that the color of something is not the color it absorbs. It's the color that it reflects. So like plants, right, leaves are green. They use light for photosynthesis. The only light they don't use is green light. So they use all of the other light because green is actually a super rare color in nature in terms of emitting light. Part of that has to do with the sky filtering out a lot of light. So the sky is blue because that's the wavelength of light that gets through the sky. Or that's the light that gets scattered. Anyway, so if you see a red shirt or the red light from this projector, it's reflecting off the board, and the only light that's reflecting off is red, or some combination of wavelengths. So we talked about wavelength. That's that's the distance between wave crests. We also can talk about electromagnetic radiation in terms of its frequency. So if we look at some electromagnetic wave, the frequency is the number of cycles or crests that pass through a stationary point in 1 second. So if this wave is moving, how fast it moves, how fast those crests pass that line that I drew determines its frequency. Frequency and wavelength are related because light's always traveling at the same speed. So if you have a longer wavelength, I can draw. So if we have a longer wavelength, that wasn't super great, but it's good enough.
May I have your attention, please? This is Atlas IEP.
So a longer wavelength on the bottom compared to a shorter wavelength on the top. If we pass this through that line, you can see that fewer crests on the long wave cross in the same amount of time. Wavelength, frequency, they're related. Inversely related. So as your wavelength goes up, gets longer, your frequency goes down. You have fewer waves per second. So those are sort of the ways we describe the wave-like properties of light. Light can also be viewed as a stream of particles called photons. So those photons are, or a particle of light is like a single packet of light energy. The amount of energy carried in the light packet depends on the wavelength of the light. So a shorter wavelength is greater energy. So light waves carry more energy if their crests are closer together. You can think of this as like waves hitting the beach. Rather than having occasional waves hit the beach, imagine if they were like hitting super rapidly, like over and over and over waves hitting the beach. Yeah, so more waves, more energy. So the relationship between these, we have a long wavelength, we have low frequency, and low energy. If we have a short wavelength, we have high frequency and high energy. So if we zoom in on this chart here, this visible section right here actually is magnified from where it actually is on the spectrum, which is this very, very small portion. So most of the electromagnetic spectrum is invisible. Tiny piece of it is what we can see. So in terms of low energy to high energy, this is low energy on this side, high energy on this side, and the numbers here are given as the wavelength in meters. So radio waves, or the frequencies that your phone uses, also in the radio wave sort of spectrum. Those are already all the way out here at anywhere from 10 to the minus 1 meters, which would be 10 millimeters. 10 to the minus 1 be 10 millimeters, all the way out to 10 to the 5 meters. And actually 5G, the really, really high capacity, high speed 5G, is called millimeter wave because those wavelengths are about 1 millimeter. So if we're moving up in energy, so low energy, radio waves, we move up a little bit, and microwaves actually occur here before we get to infrared radiation or even visible light. The reason that microwaves heat things up is because they are the same frequency as water's vibrations. So whenever you turn your microwave on, it's causing the water molecules in your food to vibrate faster and thereby heat it up. Then we have infrared radiation, which is actually heat. We'll talk about that more. Visible light is obviously what we can see.
May I have your attention, please? This is Atlas
And then, this is what I was talking about with wavelengths of different colors. So a really dark red would be like 750 nanometers. Like a green would be 550 nanometers, and then violet all the way up to 400 nanometers, or all the way, sorry, down to 400 nanometers. Higher energy, smaller wavelength. And then we get to ultraviolet light, which causes sunburn. X-rays, which we can use to see bones and other things. And then gamma rays, which are the product of radioactive materials primarily, at least on Earth. I have some more slides here to talk about those. But yeah, one of the things I do want you to be able to do is, like, if I said organize these types of electromagnetic radiation by increasing energy. So you'd say increasing energy means start with the lowest, go to the highest. So radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma. Get the idea. Starting from the highest end energy, gamma rays, again, produced by stars, radioactive isotopes on Earth. X-rays, which pass through many solids, pass more easily through, pass less easily through bones, more easily through the other meaty bits. And you can use them for destroying tumors, actually, because they do. Every time you get an X-ray, you're getting some dose of radiation, which is why you shouldn't get too many X-rays. But doctors track that kind of thing. They're energetic enough to damage biological molecules. So if you do have a tumor, hopefully you don't, they can use X-ray or gamma beams aimed at cancerous tumors to destroy them. And what they do is they take multiple weak beams and direct them from multiple angles, that's what these are, so that the tissue around only gets low doses of radiation, but where they cross delivers a very high dose of radiation. And then that damages the molecules within the tumor cell that carry genetic information, so DNA. And then those tumor cells can't replicate, and so they die. So healthy cells sustain damage also, but if you're to the point where you need to get radiation to get rid of a tumor, that's a very, very reasonable risk compared to getting rid of the tumor. Ultraviolet or UV light, right? That's why we wear sunscreen. Produces sunburn or suntan. Has less energy than X-rays. And one of the things, I guess we won't get to this really until chapter 17, but one of the other properties of electromagnetic radiation is that the lower the wavelength, the less it can actually pass through things. And deal damage at least. So UV light can deal damage to your skin, but doesn't deal any damage to the cells underneath your skin, whereas X-rays will pass right through. Visible light doesn't damage biological molecules, but it does cause molecules in our eyes to rearrange, which creates a signal that our brain interprets as vision. And there's a really cool book by Oliver Sacks. What's it called? Basically, there's an island in the Pacific, and he went to this island. He was like a neurologist. And they have a really, really high percentage of people who are totally colorblind. So our eyes have two types of cells for seeing things, cones and rods. The cones see colors, the rods see just like black and white brightness. So there's a whole population of people who can't see any colors, everything's perfectly black and white. So we went there to study that. But there are also people, primarily women, because, anyways, genetics, who are tetrachromats, who have 4 cones instead of 3. So you can see like billions and billions more colors than most people can. You can imagine like color matching would be horrible if you had to repaint. Either that or you'd be really, really good at it. But a lot of people will go their entire lives without knowing, because how would you know? So yeah, that's red. Infrared light is the light you feel when you place your hand near a hot object. So everything's emitting a little bit of infrared light. The hotter things get, the more infrared light they emit. So this is why you can use infrared sensors in night vision technology to see in the dark. So it's usually like the green and black kind of thing from movies.
May I have your attention, please? This is Atlas IEV.
The infrared photograph shown here is one that's colorized to show points that are emitting more infrared light that are hotter versus points that are colder, emitting less infrared light. And the James Webb Space Telescope that went up, finally went up into space around Christmas, is actually an infrared telescope that'll be able to peer all the way back into the beginnings of the universe. But because everything emits infrared light, they had to build a special heat shield, and they put there are things called Lagrange points. So it's always on the opposite side of the Earth from the sun. And then they put a heat shield to block any other radiation from the Earth.
May I have your attention, please? This is Atlas IEV.
Yes, it is. Anyways, very cool telescope. A lot of the way it was designed was to block infrared radiation from anything. Yeah. All right, then we go to microwaves. So the reason microwaves heat things up is because they are efficiently absorbed by water, not because it's necessarily very high energy radiation. Then regular radio waves are used to transmit signals by AM, FM, and I love that it says this, cellular telephones. I haven't heard that in a long time. So your cell phones use radio waves. And actually, when you tune to a different particular station, that is the frequency of the radio wave that you're tuning into. It's 101.1 is 101.1 megahertz. So it's 101.1 million waves per second. Okay, so talked about wavelength, frequency, and energy per photon now. Remember that frequency and wavelength are opposite. I think the easiest one to relate is high frequency means high energy. So high frequency, high energy. Why can't I spell? Because somebody's getting a massage. So let's actually start with C here. So comparing green, red, and blue light, which of those has the highest energy? Red actually has the lowest energy. Blue has the highest energy. So if you think about, try to keep in mind for particular colors, infrared is lower energy, ultraviolet is high energy. So those border, let me go back to it. So infrared is on the red side of the visible spectrum. Ultraviolet is on the violet side. And then it goes Roy-G-Biv from red to violet, which is red, orange, green, blue, indigo, violet. Okay, that'll get us started though. So if we have increasing order, I guess I said the highest one first. So we're going from lowest, and then we're going to get the highest. So blue is our highest energy. And on an exam, I would give you something laid out like this. I would say, this is the lowest, this is the highest, and then put greater than signs or less than signs. Okay, so blue is our highest energy. What's our second highest energy? Green. And then that leaves red. So in terms of frequency, which of these is the lowest frequency? It's red again, yeah. So remember, high energy is high frequency, high energy. Those two are directly related, so they'll be the same. So you can follow this same pattern here, red, and then our second highest will be green, and then blue. What about wavelength now? Our lowest wavelength, or our smallest wavelength. Yeah.
So when you say smallest, do you mean shortest, correct?
Shortest, yes. That's lowest, shortest.
Blue?
Would be blue, yes. So it would be blue, and then what? Green. Wow, I am not going to win the spelling bee. So I guess this should be short and then long. All right, so that's all of that to kind of cover the first starting point for what scientists saw in the Bohr model, or to get to the Bohr model of the atom. So like if you put neon lights have neon gas in them, at least the bright orange ones. This is bright orange part. That's actually neon gas. To get other colors, you can use other elements. So neon absorbs it and then emits it as that bright orange light. A mercury lamp will appear blue, and a hydrogen lamp appears pink. If you remember, we talked about white lights like these produce all of the colors in the spectrum, visible spectrum. These lamps don't do that. So when you take a hydrogen lamp, for example, the one used here, and you shine it through a slit, like we did with the prism before, shine it through the slit and then through a prism, when it separates out the different wavelengths of light, you only get four. You get four, actually. This one's real hard to see at the bottom there. So you get this reddish one, blue, an indigo, and a violet. And those four frequencies of light are specific to hydrogen. Every sample of hydrogen will produce those lights, or those colors. All right, so the white light spectrum, all of them. Hydrogen has only those four. Helium, I don't know if you can tell, but that one's a little bit different than hydrogen's. And then it has like a yellow, and then a sort of turquoise. I know it's turquoise, but turquoise is more fun to say. And then these other colors. And then neon has even more colors in it. So these are called the emission spectrums. And so each individual element has its own special emission spectrum. So of course then the question is, okay, but why? Why does hydrogen only emit 4 different wavelengths of light? Why does neon emit a whole bunch? Sorry, go back here. Neon still doesn't emit all of them. There's still only select wavelengths in there. If you have a good enough prism, you could actually do this with the neon light. So Niels Bohr developed a simple model. He said, okay, what if we have a nucleus and then we have these orbits? So in this model, those are specific, exact paths that the atoms take around the nucleus. And the n equals 1, 2, 3, 4, 5 indicate different levels of energy. So in his mind, he said, okay, well, if there are only certain frequencies of light, then maybe the energy of these orbits is quantized. So it's kind of like I don't know if that's a perfect example, actually. It'd be kind of like the moon orbiting Earth. Essentially, when you get any number of bodies in motion around a certain thing, there's only certain paths that they can take, otherwise they'll fling each other out of orbit. But here, I think it's a better example, is like a ladder with uneven rungs. So if you're climbing up a ladder, regular ladder, you can only stop on a rung. You can't stand in between the rungs. Unless you've got really strong arms, then I suppose you could hold yourself there. But for this example, we have an unevenly spaced ladder. So these are the different orbits, have different energies, like rungs on a ladder. You can only be in one or the other. You can't be anywhere in between. So he gave these orbits numbers, n equals 1, 2, and 3. And this idea of having these fixed energy levels means that they're quantized. The process is called quantization, and they're specified by quantum numbers. So then this explains why we only get certain wavelengths of light, because if the electrons can only move between these orbits, so if an electron jumps from n equals 1 up to n equals 3, it takes a certain amount of energy for it to get there, but the electron doesn't want to stay there, so it wants to relax back to its ground state. It wants to relax back to n equals 1, and to do that it has to emit some amount of energy, and it does that as light. So he said those wavelengths of light that we see from the prism are related to electrons jumping to certain energy levels and then relaxing back down. And he called that energy, that amount of energy, was a quantum of light. So the light emitted by excited atoms, again, consists of lines, specific wavelengths, because we're moving from specific orbits back down to a specific orbit. So you only get certain jumps because there's only certain amounts of energy that can do that, certain transitions that can take place. So the Bohr model was great as long as you were talking about hydrogen. It's kind of like, I don't know if you know this quote by Henry Ford, who started like Ford Motors. He said, you can have any color you want as long as it's black. Because when he first started making cars, they were all black. So the Bohr model is great as long as it's just hydrogen. It didn't work, though, for other elements. So predicted the lines of hydrogen, but failed for other elements. That's where scientists realized we need something better, and eventually got to the quantum mechanical model, which is all based on crazy math. So it replaced the Bohr model in the early 20th century, not too long ago. The revolution was, it's actually a funny word to use there. It was revolutionary because electrons do not behave like particles flying through space. So instead of thinking of these as like discrete little like moons to the nucleus orbiting around, it replaced those orbits with quantum mechanical orbitals. And orbitals represent probability maps that show a statistical distribution where the electron is likely to be found. So rather than saying it can be found in that specific spot, it's in this area. It's kind of like my cats at home. They have specific spots that they like to hang out, but they could be anywhere. So the Bohr model was like predicting the path of a baseball. It was saying if the pitcher throws it with this much speed in this specific way, it will travel along this exact path and end up in the catcher's glove. The quantum mechanical model said, well, actually, if you throw that electron, it will not land in the same way every time. It'll land somewhere different. So if you wanted to try and predict where that electron was going to land, like predicting where my cats are, you have to plot out all of the places that they could be. So instead of being just one baseball thrown and being able to predict if you throw the baseball the same way every time, you have to throw 1,000 baseballs and start keeping track of where they go. And you'll end up with most of the baseballs in the center, and then fewer and fewer baseballs as you go out from there. This is part of the wave-particle duality of electrons. So where a particle, baseball is a good example of a particle, you throw it, you know where it goes. Waves don't have like a set location. So an orbit is a circular path. So in the electron's motion around the nucleus, it's predictable. An orbital is a probability map showing the relative likelihood of an electron being found at various locations, which is completely unpredictable. To put it into simpler terms, a orbital is like having a good idea of where it is, which happens a lot with my keys in my wallet and my phone. They're probably still in my jeans, but they might not be there. It's unpredictable. All right, now we're getting into where we can actually start doing something with this. I'm not going to make you learn all kinds of crazy math. Not going to do any of the quantum mechanical stuff, except knowing that there's a difference between orbits and orbitals. And we're going to be working with orbitals. So we can describe different orbitals essentially by using their address. The first part of that address is the principal quantum number, and it specifies the principal shell of the orbital. So that's kind of like the town that it's in. So principal quantum number, which is n, and we have n equals 1, 2, and 3, with energy increasing as n increases. So as you get to larger and larger orbitals, you get more and more energy. Then the neighborhood of that electron, because we'll be talking about where electrons are, is the subshell. So principal quantum number gets you to like the city or town. The subshell gets you to the neighborhood. And it specifies the shape of the orbital. And those are indicated by letters S, P, D, and F. So we'll always have a principal quantum number and a subshell. And that'll tell us where to find our electron. So we describe the, well, this is the 1s orbital, right? It's kind of like the, well, it's like if you did the whole pitcher thing, throwing the baseballs, but in 3D. So not only are they landing sort of in the strike box or not in the strike box, if you're familiar with baseball terminology, but they can land behind the catcher, in front of the catcher, they can land behind the batter, all over the place, but in 3 dimensions. So it's like a sphere. Yeah, and as the dots get, well, they represent it, dot density represents the probability of finding an electron. So if there are more dots, you're more likely to find an electron there. So we can represent orbitals with geometric shapes. So for the s orbital, all of the s orbitals are the same shape. They're all spheres. And in these representations, the sphere represents the volume within which, so where you would find the electron 90% of the time is inside that sphere. There's still a 10% chance that it's outside the sphere, but most of the time in the sphere. All right, so the single electron of an undisturbed hydrogen at room temperature is in the 1s orbital. This is called the ground state, or the lowest energy state. And electrons are really lazy. They like to be in the lowest energy orbital available. They like to be in the ground state. I think cats act a lot like electrons. So this is like my cat Mochi. If most of the time he's in the ground state, laying on the ground on his back, twisted. And then you can get him into a higher energy state by giving him catnip. Or sometimes just at 3 a.m. for no reason. So the absorption of energy would be the catnip for Mochi, can cause the electron to jump to a higher energy orbital. The excited state, which is highly unstable, just like cats on catnip. And all atoms have one ground state, many excited states. So we're always going to be jumping from some ground energy state up to something higher. All right, so like I said, all of our s orbitals are spheres. When we go from n equals 1 to n equals 2, we now have a kind of like Russian nesting dolls. We have a sphere and then a sphere on the outside of that. So spheres and spheres, those are the s orbitals. The 2s orbital is higher energy and slightly larger than the 1s. That's the easiest shape. The p orbitals, so our first p orbital is at 2p, has 3 separate orbitals in it, and they're all this dumbbell shape. So they're existing in 3 dimensions. So you've got 2, you can imagine 2 of them are crossed on the ground, and then 1 is standing up, intersecting those. They have different orientations and don't overlap. The thing I want you to remember here is that they have a dumbbell shape and the same energy. So all 3 of those 2 p orbitals are the same. Just like with s orbitals too, if we went from 2p to 3p, we'd have higher energy, but it'd be the same shape, and then it would be dumbbells inside of dumbbells. So the number of subshells that we have in a given principal shell is equal to n. So for n equals 1, we have s. For n equals 2, we have s and p. And then 3 is sp and d, and 4 is sp, d, and f. In the n equals 3 principal shell, we have 3 subshells, s, p, d, and d. S and p contain 3s and 3p orbitals, which are, again, the same shapes to 2s and 2p orbitals, but slightly larger and higher than energy. And these all exist at the same time. They're not like separate things. So if you were to draw out something, if we were to draw out the n equals 3, we would have our 1s, and then we'd have 2s, and then we'd have 2p, and then we would add d on top of that. Well, I guess there would be 3s, and then 3p, and then d on top. So the d orbitals, if you went from a sphere to dumbbells, now each d orbital has 2 dumbbells that are crossing. So we got the x's, and then my favorite, which is the dumbbell with the donut. This one's really interesting to me because the donut and the dumbbell are not connected. And your electron can be anywhere in there, but it can't be in between. But it can also travel from, let's say, here to over here without crossing the space in between, which is super weird. Again, quantum stuff. So it can't cross those. And then even with these orbitals, you can go from one of these dumbbells to another without crossing the space in between. It just appears in one spot or the other. All right, so electron configurations are essentially us writing down the address for electrons in an atom or around an atom. So for ground state hydrogen, that looks like this. We have 1s, so n equals 1 principal shell, s subshell, and then this superscripted 1 is 1 electron. So if we're going to draw out or write out an electron configuration for helium, we'll be switching back and forth between the periodic table here in a little bit, but helium has 2 electrons. So it would also be 1s and then 2 electrons. So instead of the 1 electron of hydrogen, helium has 2. Okay. We also have orbital diagrams, which is very, very similar information, but shows the electrons as arrows in a box or on a line, representing the orbital. So for hydrogen, 1s, so this is our 1s orbital, and there's 1 electron in that orbital. For helium, we'd also just have a 1s orbital, but we would then have 2 electrons. So in our orbital diagram, I drew the electron as that little half arrow. It's not a 1, it's a half arrow. But that represents the electron's spin. So this electron has up spin, and if we put 2 electrons in an orbital, the other electron would have down spin. So that's an arrow pointing down. This is called the Pauli exclusion principle, that orbitals may hold no more than 2 electrons with opposing spins. So you won't have 2 electrons with up spin or 2 electrons with down spin until you take more advanced chemistry. Maybe not even then. So not these. We already did helium. We're going to write an electron configuration for helium and for lithium, and then we're also going to do an orbital diagram for each of those. Okay, so question, how do you determine how many electrons an element has? Yeah, the periodic table. What about the periodic table? Close. It's actually on every box. Yeah, the atomic number. It's the same number of electrons as the atomic number. So for helium, we have 2 electrons because it's atomic number 2. For lithium, we'll have 3 electrons because it's atomic number 3. Oh, right, my mouse is over there. All right, so we know helium has, not 1. Sorry, 2 electrons, and lithium has 3 electrons. So then our orbital configuration for helium is going to be 1s2. So we're basically placing the electrons into orbitals, and we keep placing them into higher and higher energy. So you always start with 1s. And then, so for helium, still have 2 electrons. We can place both of those electrons in the same orbital together. So you can have 2 electrons per orbital with opposite spins. So then for lithium, we can start the same way. 1s2. But now we still have 1 electron left over. So where would we put that? We move up to the next orbital. Well, we'll cover that in a second. So basically, if you filled up all of our 2s, we just go to the next highest energy orbital. So in this case, it would be 2s, and we have 1 electron left to place, so 2s1. When you write out the orbital diagram, we have a 1s orbital, and we'll fill that up. And then we'll move to a 2s orbital and put our 1 remaining electron in there. So our electrons then, we always figure out how many electrons we have, and then we place them into orbitals in order of increasing energy. So start with the lowest energy, go to the highest energy. This is a chart that shows that energy levels. There's an easier way to remember this, though. So we started with 1s, and then with lithium, we moved up to 2s. And if we had had more electrons, we would place them into 2p, and then 3s, and then 3p, and then 4s. And you'll notice that we skipped 3d, because 3d is a higher energy orbital than 4s. So that's actually, instead of doing this on this slide, I'm going to do it back on the other slide. So we want to write the electron configuration and orbital diagram for carbon. Let's go back over here. So we want carbon. I'll go to the periodic table. Carbon has how many electrons? 6. So we've got 6 electrons. So we've got 6 electrons that we need to place. So we'll start with, goes up here. We'll start with 1s, 2. Then we'll do 2s, 2. Because each of our s orbitals can hold 2 electrons, and each of the p orbitals can hold 6 electrons. So after 2s, the next highest energy orbital is 2p, and it'll get 2 electrons. So that's describing then, if we were to put these electrons into here, it'd be 1, 2, 3, 4, and we go 5, 6. We'll get into why they don't share boxes. They don't share boxes until they have to. So for an orbital diagram, I'll do that over here, actually. So we'd have carbon, and then you can do lines like this. So this would be 1s, 2s, and then 3 lines together would be 2p. And so it fills up the same way. 1, 2, 3, 4, 5, 6 electrons. Oh yeah, it was on this slide. So Hund's rule is why we fill orbitals singly first, or one at a time, with parallel spins. So all pointing in the same direction. So they could all be going up, they could all be going down. All right, so this is the Quantum Hotel, a discount resort for electrons in Mrs. K's chemistry land. This is my mom's hotel. The first floor has, I guess it could be my wife's hotel too, but my mom teaches chemistry, so it's my mom's hotel. The first floor has one room, that's our s orbital. The second floor has two rooms. It has one s room and one p room, or s and p orbitals. The third floor has three rooms, s, p, and d. And then each room has one bed, or each s room has one bed, each p room has three beds, and each d room has 5 beds, and f rooms, which we won't get to in this class, but they have 7 beds. You can only have 2 people for bed, hotel policy. And they have to sleep opposite, so head to foot, also hotel policy. So this essentially explains the rules for, or is a nice analogy for how we fill these in. So if we were to take, let's pick another element here. Let's do, let's do oxygen. So we'll do oxygen. So oxygen has 8 electrons. So we come back here, we have oxygen with 8 electrons. As we're checking in these people to our hotel, we fill up the rooms one at a time, starting from the first floor and going up. And we want to fill these up first. So we fill in the first floor 1s room, then we fill in the 2s room. So now we've used 4 people. Now our 2p room has 3 beds. So we'll assign each of those people at first, 1 bed at a time. But somebody's going to have to double up. So it doesn't matter where that doubled up electron goes, as long as it has the opposite spin. Which, you know, in my mind it makes sense, because if you go to a hotel room with somebody else and there's, well, if you go to the hotel room with a friend, then you're going to probably not share beds. Depends on what kind of friend. If you were to go to a hotel with a coworker on a work trip, you wouldn't sleep in the same bed. Anyways, the idea is, if you can sleep in your own bed. And electrons are the same way. All right, so this is one way for figuring out how to fill these orbitals. So the left here, this is just a list of 1s, 2s, 3s, 4s, 5s, 6s, 7s, right? Just goes counting, well, goes down, counting up. Then you put next to that the p orbitals, which start at 2p. So at 2s, you also have 2p, and then use 3, 4, 5, 6, and then 3, or the d orbitals start at 3. So those line up starting there, and then f. Then when you fill in your electrons to orbitals, you go at an angle like this. So we start with 1s. We can put 2 electrons there. Then we go to 2s. Once that's filled, we go to 2p, and then 3s. And then we go to 3p, 4s, and then we start 3d, 4p, 5s. Writing it out this way helped me a lot in remembering that we go from 4s, 3p to 4s, and then 3d. It's also on the periodic table. Not quite as clear. But each period on the periodic table, so that's the row. Line this up nicely, okay. This corresponds with the principal quantum shell. So the first row on the periodic table is hydrogen and helium, n equals 1. Those are both s block elements. So their highest energy electron is in an s orbital. And that goes for all of these elements. For elements in the first column, they have 1 electron in an s orbital. For the 2a elements, they have 2 electrons in the highest energy s orbital. Over in the p block, these all have their highest energy electron. So the last one you place will be in a p orbital. And then for the d block, the d orbital, and then we won't get to f. But so let's look at our example of, let's do carbon again. So carbon has 6 electrons. And based on where it is on the periodic table, we know that we're going to end with our last electron in a p block. And even more specific than that, we're going to have 2 electrons in the p block, because it's 2 elements into the p block. So this is kind of like a cheat sheet run, right? So we know that it's going to end with 2s, 2s2, 2p2. But it's going to start 1s2, then it'll go 2s2. So 1s2 is these 2 electrons, or those 2 electrons are represented by hydrogen and helium. And then 2s2, that's lithium, beryllium. And then carbon would be 2p2. So anywhere that you stop on a electron configuration is going to be a different element. And so you can kind of just count the elements here and say that, okay, that's 1s1, 1s2, 2s1, 2s2, move over to p, p1, p2, p3, all the way through. The only thing that you have to remember is that when you get down to 4, we go 4s1, 4s2, but then the D block is off by 1. So this is, you see scandium here, is 4s2, 3d1. So it goes 4s, then 3d. If you go down to the next row, we have 5s1, 5s2, and then this one is 5s2, 4d1. So D block is always 1 less than the row that it's in. All right. Does that make sense? Do you feel like you could do an electron configuration? Maybe. Maybe we should do some more examples. We've got a bit of time. So lower energy orbitals fill before higher energy orbitals. Orbitals can hold no more than 2 electrons. They have to be opposite spins. If we have orbitals of identical energy, so like the p block or p orbitals have 3 orbitals, then we fill them in one at a time with parallel spins before matching up with opposite spins. All right, so let's write electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. So we got nitrogen. How many electrons? Well, we're going to do nitrogen, oxygen, fluorine, and neon. All right, so we're going to have 7 electrons, 8 electrons, 9 electrons, and 10. So I'll write that in over here. This is going to be 7 electrons. Yeah, oxygen is going to be 8 electrons. Fluorine is going to be 9 electrons, and neon is 10 electrons. All right, so for nitrogen, what is our electron configuration going to look like? Yes, you'll always start with 1s. We'll talk about shortcuts later, but always start with 1s. And how many electrons can be in an s orbital? 2. So that's 1s2. And then we go to the next orbital, which would be 2s. And that's 2 more electrons. So we've used 4 of the 7. So we started with 7 electrons. So yeah, 2 electrons each. Then we go to 3, or sorry, not 3. We go to 2p. And actually, let me flip over to the periodic table here. So we did 1s, 2. So that's, I'm going to say that this is hydrogen and helium. So hydrogen would be 1s1. Helium would be 1s2. It's 1 electron, 2 electrons. Lithium would be 2s2, or sorry, 2s1. Beryllium would be 2s2. So now we fill in the p electrons, which there are, we can put 6 electrons in a p block. So counting from boron to neon is 1, 2, 3, 4, 5, 6. So how many electrons then are we going to have in our 2p orbital?
We're trying to get 7, correct?
Trying to get 7.
So we have 4, 3.
Yeah, so 3. And again, one of the a shortcut that you can use on the periodic table is that nitrogen is the 3rd element from the left in the p block. So all of these are the p block. All of these are the s block. And then again, these are the d block in the transition metals. So for oxygen, how many electrons is it going to have? 8 total. Yes? Sorry, I wasn't clear. But you're right, 8 electrons total. How many electrons in the p block? It's the 4th element in the p block.
Oh, so 4.
So 4 electrons.
But it could hold up to 6, correct? Because
Yeah, the p block can hold 6. But again, we have to start at 1s.
okay.
So we'll start at 1s, and this will be the same. 1s2, 2s2, and now 2p4. And then if you add up all of the superscripts, so 2 plus 2 plus 4 gives us all 8 electrons. We'll start with 1s, and then if it's hydrogen, it'll be 1s1, and helium will be 1s2. But then everything after that, yeah.
So for the 2p, the p block, we put 2p to the 4 because it was the 4th one in the p block, right? In like the row wise, like the 4th one down.
Yes, I guess it's more that corresponds to the number of electrons you have left over after filling in 1s2 and 2s2.
Yes.
Yeah, so those are the same. Okay, so now we're doing fluorine. So what is our, well, let me go back to this. What's our electron configuration for fluorine going to be? 1s2, 2s2, 5. So really, the electron configurations are the same for the most part. So for neon, what would it be? 1s2. Yep. 6. So it goes in exactly the same order every time. If it goes longer or farther down on the periodic table, there's going to be more stuff to fill in. So by the time we got into neon, you've completely filled in the 2p, or the 2, n equals 2 principal shell. So you can imagine, and I'm going to end with this last thought here, if you had some element like bismuth or polonium, use the mouse, right, something like way down here, it would take a long time to fill in every single electron, because it's got lead has 82 electrons. So you'd have to write 1s2, 2s2, 2p6, 3s2, 3p6, going all the way down, and you get to D, which each of those has 10 electrons in it. So as chemists, we're lazy, and we're lazy in a very reasonable way, though, right? Nobody needs to do that. To quote the old meme, ain't nobody got time for that. So what we do is we say, we're going to start from one of the noble gases, because that represents basically everything before that is completely filled up, so we're going to start from there. So if we wanted to do lead, and actually let me just do lead for you real quick. Actually, I need to look at, we would start with, we'll basically go back to the next row, or the row above it, and then go to the end and say, we're going to start with xenon, because we've got all of the same electrons as xenon, plus some, and we can fill those ones in for a single row. Oh no. Yeah, I'll do lead. Lead has, no wait, I don't think lead has F, because F comes after 4D, 4F, which is 5. But, oh, sorry, periodic tables here.
May I have your attention, please? This is Atlas.
Yeah, it does have D, or it does have F. That's fine, we'll do lead. So lead would be, oh, we didn't do orbital diagrams. It's okay, we'll do those next time. It'll be a good refresher. Lead would be xenon, and you write the element in brackets. That says I'm starting here with this electron configuration. And then it would be 7s2, let me just double check that it was 7, 6s2, sorry. 6s2, 5d10, 5, I believe it would be 5f14, and then 6p. So it's 2 in here, so it would be 6p, 1, 2.
So it goes in the order of the periodic table?
Yep.
Letters?
So 6p2. Mm-hmm.
So I have a question. So you did 6s2 and then 5d. So like the letters, right?
Mm-hmm.
So isn't it like S and then I don't know P and then D, right? That's kind of like the order. Or so why are you using F, because they could hold more?
Oh, it's 4f. Yeah.
Or does it go? I don't know. Does it go?
So this is where moving into the D and F orbitals, D is, and actually we can go to this one. This doesn't have F orbitals on it, but we're filling them up in order of increasing energy. So that's what this increasing is here. All right, so as we go up, that's more energy. So 1s is below 2s. So we go to 2s. The next highest one is 2p, then 3s, then 3p, and then 3d is actually higher than 4s. So we go to 4s first before we go to 3d. Then we go to 4p, then 5s, then 4d. And then you would go to 6s, 5d, 4f. So 4 would be, again, F would be offset by 1, just like D is offset by 1. I'm not expecting you to do the F orbitals. But this also, if you write this guy out, that's 1s, 2, 3, right? So you can write this out on a test or something, and then you start on the corners. And so you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p.
May I have your attention, please? This is Atlas IED.
6s, and then it goes 4f. Yeah.
For the future, would you say this would be a good thing to write on our index card?
Either write it on your index card or just remember how to write it. This is like, actually, here's a test taking strategy. There are some things that are harder to keep in your mind for a long time, but you can keep them in your mind for a short time. So that's the kind of thing that you would look at right before you come to the classroom or whatever, before I hand you the exam, and kind of get that in your mind. And then as soon as you get the exam, flip it over, find a blank spot, and write that thing down. So this would be that kind of thing. Now this is systematic in that you start at 1s. Right, so this whole row is n equals 1, n equals 2, n equals 3, and so on. It's just the order that you go through it as at that weird angle. I won't give you anything as low as F. I'll probably give you a D orbital, but yeah. Any other questions about these? The periodic table can help you out a lot with these kind of things. Okay.